Robotics 314 React here, and today we are looking at Port Royal. I think I've previously called it Port Royale in previous videos, but it's just Port Royal, and I may make the mistake again in this video, so do forgive me for that. So we're going to do what we usually do. We looked at the demo at the start there. We're going to look through some of the settings, some of the engine, and we're going to look through the technical documentation, look into a bit of how ray tracing works versus rasterization. Then we're going to look through the graphical test, and then we're going to compare with some of these settings on or off, how it looks, how it runs. And this is part of my series of going through 3DMark's. So you'll see in the description the previous videos that we've had. It's probably going to be a few more as we work through the ray tracing benchmarks on this latest 3DMark, and then I'm going to try and get a video on 3DMark 99, which should conclude the series, but we probably will revisit 3DMark in the future at some point as well. So make sure to drop a like and a subscribe for more content on graphics and tech projects, as well as general video game videos. And let's move on with the video. And here we are in the documentation. First thing to note, that this was released in January 2019, very shortly after the release of the RTX cards from NVIDIA, which marked the beginning of the real-time ray tracing age in video games. So it was one of the earliest benchmarks to come in and test ray tracing with that new hardware. So of course I'm running this on a Ryzen 7700X with an RTX 4090 and 32GB of VRAM. So we have the pretty much the basics here: platforms, Windows, GPUs that supports DirectX ray tracing. So that means DirectX 12 feature level 12.1. So there's just a little bit here about announcing DirectX ray tracing, how it affects shadows, reflections, and other effects that are difficult to achieve with traditional techniques, i.e. rasterization. So there's an additional blog post here where they talk about how 3D graphics works in a traditional sense and also how ray tracing works. Now essentially rasterization is just taking the data from the scene, running some calculations based on where things are in 3D space, where lights are in 3D space, and then coming back with a calculation. Now it's not exactly perfect, but it runs fast enough and is enough to get a color to a pixel, which means you can render out to the screen. Now this is where ray tracing comes in, and you can actually do a much more advanced calculation that traces the path of a ray to simulate light in the real world and get a much more realistic pixel back by tracing that ray from the camera to a light source while bouncing off of various objects in the 3D scene. So I'll put a link to this in the description, as well as a global illumination video done by Digital Foundry that really helps give a good intuition of the difference between rasterization and ray tracing. So the ray tracing in Port Royal, it uses DirectX ray tracing for reflections and shadows, which means I don't think it's using it for ambient occlusion. It uses DirectX ray tracing to produce realistic specular reflections with the correct perspective. Ray tracing overcomes a limitation of traditional techniques by accurately reflecting objects that appear outside the screen space and that are occluded by other objects in view. And it also uses the ray tracing to produce pixel perfect hard shadows. You can actually look at some of the benefits of ray tracing here with Metro Exodus. Here's the original 2019 version of rasterization. Here's the 2019 version with just RTGI applied, and here's the fully ray traced 2021 enhanced edition. You can see how much better things get when you're using proper lighting calculation. You can see here the lighting is a little bit inaccurate. There's way too much specular in this corner. It doesn't quite work. There's not much realistic shadowing on that person, on that body, so it doesn't quite look right. Here things improve a little bit. You've got a little bit of extra definition in the shadowing here, a little bit more realistic bounce lighting, but then here you have really realistic shadows, really all blends together perfectly because it's all part of the same algorithm. The bounce lighting looks much more realistic, and the shadowing is much more softer, and the lighting is much more softer and realistic. You can also see here's the 29 version with RTGI on, so that's just the bounce lighting being handled by the ray tracing, and here everything is being done by the ray tracing, as well as probably an enhanced version of the GI being done in ray tracing. And you can just see how it takes that same scene, the same models and set geometry, but greatly enhances it. You can just see the light is much more realistically bouncing off of the table there through the window, creating much more realistic shadows, and depending on the materials, much more realistic lighting bounces off of them. So you can see the advantage here of ray tracing. Now what this also means is the reflections are a lot more realistic. So previously in stuff like the Source engine, I believe there is planar reflections being used, which is essentially we are just re-rendering the scene in a reflection, which is great. It's quite accurate enough, but it can be quite expensive, and it doesn't quite work on all varied shapes and sizes of objects. So it works perfectly fine for a flat space of water like here, and you can sort of disturb the reflection using pixel shaders, but it can be quite expensive, as I say, and it won't work on all surfaces. So there is another way of doing it called screen space reflections, which uses data on the screen to inform the reflection. Now you can see screen space on the left and planar on the right. And you can see the limitations of screen space here. It gets blurrier the further you go upwards because it's having trouble determining where that item is on the screen and then reflecting that downwards. And the more things go off screen, the more will disappear off the reflection, because of course it can't use data that's off screen. So that's where you have to have either the reflection just completely disappear, which looks horrible, or you have a cube map fallback. It can also result in a lot of errors and weird blurriness. I think even in PUBG, in the older versions, you would have your gun reflecting in distant water. So that wasn't great because it wasn't doing the proper depth test to determine that the pixels on your gun are indeed nowhere near the sea that's miles away. Screen space reflection and planar are fine. Planar is quite expensive and a bit limited. Screen space gives you a bit more freedom and is a bit more performative, but it's very much inaccurate and has major limitations. So ray tracing, especially in this Port Royal video, overcomes that by pinging the ray out, calculating how it traverses the scene, pinging it back to a light source, and then calculating the image back, which is what they mean by reflecting objects that appear outside the screen space and are occluded by other objects in the view. So as mentioned, the system requirements are essentially DirectX 12 with DirectX ray tracing support on the GPU and the latest version of Windows 10 or 11 that can support this, as well as 6 GB of video memory, because ray tracing is quite expensive on the video memory. So we have the graphic test here. It's a GPU benchmark primarily, so it features ray traced reflections, shadows, ray traced and shadow mapped. So it's not fully ray traced in terms of the shadowing. Does transparent surfaces with ray traced reflections, volumetric lighting, particles, and post-processing effects. The main role of the CPU is to compose the command lists that the GPU executes. The Port Royal engine is multi-threaded and divides the work between all logical cores. So it's similar to what we've seen in prior benchmarks, where they're using as many cores as possible to feed the GPU as much information as possible. So given that this test is about 5 years old, my CPU should not be an issue here. And over to the Port Royal engine. So it uses a custom engine developed in-house with input from UL benchmark development program members such as AMD, Intel, and NVIDIA. They work with Microsoft to create a first-class implementation of the DirectX ray tracing API. So it improves on the Time Spy / Night Raid engine by implementing new effects and integrating DirectX ray tracing. So here we have information on the rendering passes, and it has a high-level construction of a typical frame in the Port Royal benchmark. Graphics tasks, compute tasks, and ray tracing tasks. So there's actually some photon mapping, global illumination here, shadow maps, G buffers, particle and fluid simulation. So you can see there's some stuff happening synchronously here. Exactly what levels they go. So it starts off here and goes down to your final scene. Post-processing. So photon mapping is a 2-pass GI rendering algorithm developed between 1995 and 2001. Light packets called photons are sent out to the scene from the light sources. Oh, so this is actually from the light sources, not from the camera. Traditionally, ray tracing is sending out the rays from the camera rather than the light sources, because if you're firing out from the light sources, you're getting a lot of rays that will never hit the camera, so it's wasted calculations. But this is actually firing out from the light sources. So whenever a photon intersects with a surface, the intersection point and incoming direction are stored in the cache called the photon map. That's especially used for caustics and for light, and then the probability for either reflecting, absorbing, or transmitting refracting is given by the material. So once a photon map is constructed, it is arranged in a k nearest neighbor algorithm to be as optimal as possible, and then it's stored for later. And then it goes to rendering, the second pass. The photon map in the first pass is used to estimate the radiance of every pixel from the output image. For each pixel, the scene is ray traced until the closest surface intersection is found. So yeah, it's using photon mapping for the global illumination. It must mean it's quite expensive if it's calculating it from the output of the lights rather than rays from the camera. So frustum lights can be shadowed. For each shadowed light, a shadow map is allocated for each frame. The maximum resolution is 1K. The shadow map is used for surface illumination, for generating light shafts for volume illumination. And the shadows are sampled in illumination, cube rendering, and ray tracing shaders. Some of the ray tracing here is being assisted by other things. So you're allocating a shadow map out for lights and then sampling them with ray tracing. So I imagine that means when a ray bounces off of a shadow map, it counts it as a shadow rather than using the ray tracing to calculate the shadow itself. I think that's just a case of this is an older implementation of ray tracing from the early days. I imagine nowadays you just calculate the entire shadow using ray tracing. Could be wrong on that. So opaque objects are drawn into the G buffer in 2 passes, separating luminous and non-luminous geometries. So it uses PBR, it uses albedo, metalness, normal, and roughness and height textures, luminance, blend, opacity, and light maps. So there's a whole load of information there in different maps to get information out on the material. Volume illumination is computed using the tessellated light volume approach. So the volume mesh of a light is computed by extruding the shadow map of a light using the tessellation pipeline and adaptation heuristics to reduce the amount of mesh data. The fragment shader then computes the volumetric illumination. So you're essentially using a shadow map from the light, so essentially a camera from the light position, I think, to get the volumetric mesh of it, and then using the fragment shader to compute the illumination from that. Yeah, using additive blending to sum up the air light integral for the view ray corresponding to the pixel. This is the only part of the rendering that uses tessellation. Nothing else in geometry uses tessellation in this benchmark. So there's certain things you can set up to assist the ray tracing. Cube maps are used to cache the radiance from both perspective correct and traditional specular reflections for static geometries. So that's illumination, and then there's MIP levels of the cube maps. So you can actually MIP map the cube map. which means reduce the detail of it the further it is away from the screen. And that looks like it's for static geometries. The illumination of the cubes is dynamically updated in a compute pass similar to the normal surface illumination each frame, queried from world space and illumination pass, and the view ray direction is set to the main camera view direction to match the specular highlights. So I think it's actually building radiance cube maps by using ray tracing each frame. Transparent geometry using order independent transparency techniques called order independent transparency approximation with raster order views. Transparent geometry is rendered and a per pixel visibility function is approximated by merging pixels into the compressed function. The transparent geometry is re-rendered, illuminated and additively blended according to the visibility function. So there's a nice little document here from Intel about that. So again, it's very similar to what we were looking at last week, where it's just a way of ordering transparent geometries. Ambient occlusion is using an adaptive screen space technique, so yeah, it's not using ambient occlusion with ray tracing. The lighting is done via compute shaders after screen space ambient occlusion and calculate unshadowed surface illumination, and it's done right after the G-buffer rendering. Reflections are multiple render passes, and they cast rays to the important sample direction for each screen space pixel that is over a roughness threshold. The resulting hit points are stored, and the results are used to sample reflections from the environment maps. In cases of pixels being non-visible from the cubes or with mirror-like surfaces that require per pixel reflections, we compute the reflections separately to render a correct reflection. For reflections of glass, we always run the full shading. So I think there's a blend here where you can actually cast a ray to get the information from a cube map and then render that back to the screen. But for times where there's nothing visible or mirror-like surfaces, as they say here, they're using the full computation to bounce that ray off onto the actual geometry. So there's certain optimizations here from what I'm reading and understanding. So the reflect pass uses the ray tracing pipeline to generate a reflection ray for each pixel above a predetermined roughness threshold. So I imagine that means the less rough the surfaces, that's where they're going to be hitting it with the rays, so shiny surfaces essentially. The reflection cubes are used for glossy reflections to find the radiance of a ray intersection generated by the ray tracing pass. The world space position of the projected point in each cube is tested to determine if it corresponds to the same intersection point or if it is occluded by another geometry. Point is not found in any cubes or screen space illumination textures. The instance ID, primitive index, and coordinates stored by the reflection pass are read and used to recompute the radiance for the given ray. The roughness of the surface is above a certain threshold. The cube sampling is skipped since the resolution is generally not enough for sharp reflections. I think what it's saying here, the rougher the surface is, the more it will use the cube reflection sampling to try and get more data to the ray tracer, because it doesn't need to be as accurate as really shiny materials, which need to be much more pixel accurate in their reflections. So that's where you do the full ray tracing path as well, and then they do a filtering pass at the end. And then there's some pre-temporal anti-aliasing passes. There's a decal system which are rendered on top of the G-buffer using compute shader asynchronously. That's what we saw in the above diagram. So we saw that in Steel Nomad, where you can just add decals to geometries, i.e. extra little things like bits of dirt and stuff like that to the textures. And the ray trace shadows. The shadows are implemented in a separate pass running an async compute queue. For each fragment, there is a shadow ray cast from this fragment in the world space towards the direction of the light source. The shader is then used to detect whether the ray has been occluded on its way from light towards the fragment. Okay, it's using shadow mapping to inform the ray tracing. The output of the ray generation shader is a shadow modulation map, which is float 32 texture filled with values ranging from 0 to 1. The values are generated per fragment by dividing energy flux that has reached the fragment by the total energy flux present in the scene from all the lights. One shadow ray is cast from each fragment towards the light source. The post-process filter is not employed for the shadow mask, so the implementation only supports hard edge shadows. So we're going to get sort of Doom 3 like shadows here, I think. So yeah, as you're going from the fragment, the pixel on the screen and the camera, to the light source, it's casting the shadow rays from there to detect whether the ray has been occluded on its way. Man, that's complicated. I wonder if that's how all shadows are done in ray tracing, or whether you can do it a different way. I imagine if you're doing your ray tracing for ambient occlusion as well, you'd probably have to do it in a bit of a different way to make sure they don't conflict and make sure the ambient occlusion blends with the shadowing, because ambient occlusion would, I don't know if you could do that using a shadow map even from a ray. I don't know. That'd be interesting to see in future benchmarks to see how they do that. I'm gonna have to try and read a bit more how about ray trace shadows are implemented as well. And again, we have GPU simulated particles using the async compute queue, and then we have something very cool, fluid simulation, which is only in the demo and it doesn't contribute to the benchmark score. And fluids are done by async compute queue, and it's based on the position-based fluids method. And there's something called Radix sort to compute the fluid particles using the Z order curve, and spatial hashing is used to accelerate the neighbor search. So I'll put links in the description to more information here. There's some information on the fluid simulation, really complicated stuff, a lot of mathematics. You can sort of see here how it's allowing for calculation of really complicated fluids to go around objects, and that's what we'll be seeing in the demo. Well, that's what we've already seen at the beginning of the video. And then Radix sort is a way of just sorting out numbers from the most important to the least important. So I think that's ordering the the fluid particles on the Z buffer to make sure the memory access is being calculated in the right way when calculating interactions, and to make sure it's most efficient, because you're going to need to make sure those particles all bounce off each other correctly in the right order. And then the liquid surface is constructed in screen space by splatting ellipsoids, doing most of the computation in the vertex shader and smoothing the result. The illumination is done a compute pass, and the illumination is used to apply approximate screen space refractions. So it looks like an ellipsoid is this kind of shape in 3D space. So again, there's another paper here. I'll link to it in the description. I think, from what I'm reading here, it's taking that shape and then getting a load of random information from it, splatting it out in that 3D shape and retrieving information back from it, which makes sense. Yeah, okay, the surface is constructed in screen space by splatting ellipsoids, so it must have some access to the depth buffer to do that. So each part of the surface will be made up with that shape, splattered out, getting the calculations back to get the surface, and then smoothing the result out. That's probably why it's not in the actual benchmark result, because it's probably got an element of randomness to it that can affect the score. So we've got post-processing here, you've got temporal anti-aliasing, post-TA stuff to handle transparent elements, depth of field, very similar to the depth field we've seen before. Bloom, same stuff we've seen before. Lens reflections, the same stuff we've seen before. And then tone mapping at the end. And then dynamic global illumination is only used in the demo. We've implemented a dynamic global illumination solution using real-time photon mapping. This is a multi-pass algorithm with components of rasterization, ray tracing, and compute work. The main passes of the algorithm are a sample generation from reflective shadow maps, photon tracing, photon splatting, and irradiance filtering. Again, that's not used to calculate the benchmark score, because I imagine there's an element of randomness to that. So with all that done, we can now look at a custom run. You've got the graphics test here, which you can't actually switch off. You have to have on. Don't know why. You can disable ray trace shadows, light shafts, depth of field, decals, transparency. You can switch things on and off. Disable bloom. Again, you've got anisotropy, anti-aliasing, sample counts, reflection filtering quality for demo, reflection filtering quality for the main test. And you've got reflection mode, no reflections, traditional, and ray traced. So I think what I'm going to do is run through it ray traced, and I'll probably disable async compute and see what the difference is, and then we'll probably take a look at traditional rendering. That's all at 4K, everything maxed out. Let's dive in. So here we have something that looks very similar to CloudGate levels of technology. Looks like it's probably set in the 3DMark universe a long time after Shattered Horizon. But here already you can see the reflections there. And you can kind of see the blockiness in the reflections there in some of the more rougher areas. And I think that's where it's sampling the cube maps for the ray tracing. Because obviously the rougher the surface, the less the reflection is going to be. So the less compute time you put into that. And then for these sort of reflections, it's doing the more sort of full ray tracing technique, I believe, from what I understand anyway. So the area, that red area beneath the ship is a lot more rough and a lot more diffuse. So you save time on calculations by sampling the cube maps. It's a bit more effective than doing the full ray tracing through the geometry. But you can see the reflections there of the ship. And then the reflections on the ship itself, on the table here. You can really tell that global illumination is kicking in and looking amazing. I said it to run at 4K, but I think that's the external resolution. I think it is indeed running internally at Quad HD. Or slightly higher. But it still looks incredible though. It just looks so shiny. But you can really tell the lack of ray tracing ambient occlusion, because it doesn't quite look as good as it could. You can see the hard edge shadows there as well. Yeah, I think if you were to fully ray trace the shadows, that would look really incredible. A lot softer, more realistic shadows. And there's the liquid simulation, which, oh man, that looks cool. Yeah, the way it's splatting out and calculating that surface has an element of randomness to it. And here we go, the working Joes. So that was the demo, now we're on to the actual graphical test. So this uses less advanced GI. You can kind of tell already it doesn't quite look as good. And it won't have the fluid simulation. Everything else should be the same. There's your volumetrics. You can kind of see a bit of the grain there. I'm not sure if that's a film grain thing over the top or whether that's part of the ray tracing limitation. But you can see there the reflections of those rings. You can't actually see the geometry of those reflections directly. You're just seeing it literally in the reflection, which shows the strength of ray tracing there, because you'll be able to sample things off screen. It just looks so good, reflections in ray tracing. Because rasterized reflections are just very limited, as we've talked about earlier. So only so much you can do with planars and screen space. And there's your transparency stuff. And yeah, those hard shadows really, I don't want to say it, but they kind of bring the quality down a little bit, because you've got the ray trace reflections, which of course is the main point of the benchmark, but having those hard edge shadows give it that kind of older technology look, rather than the really nice soft and realistic shadowing and ambient occlusion you can get from fully ray tracing everything. But of course this was the older days of much earlier technologies of ray tracing, so it makes sense. This is a custom run, so there's no score, but we have got a sort of average FPS, 35.26, and that's with async on. Now last week we didn't see much of a difference with async on or off, but I imagine because this is so much more intense on the GPU, we may see a bit of a difference this time. So the demo didn't give us a frame rate output, but the graphics test does, and we're around 30 odd FPS, maximum of 63. So it's still pretty hardcore even for a 4090, but then it's probably using older techniques, not as efficient. No Ray-Reconstruction, no DLSS. A bit of a CPU temperature jump at the start there as it's setting the scene up, and then a few jumps in between as it's handling a lot of the ray tracing execution orders to the GPU. GPU load pretty much sits at 100% with a few dips every now and then. In fact, that's when the frame rate jumps up, is when the GPU load drops and the CPU utility raises just a little bit. That must be a much more easier to run part of the scene. The CPU's not being too taxed, so yeah, it's pretty much all on the GPU. Excellent stuff. Okay, so let's run that again with async off and see what the result is. So I've run a number of tests with async on and async off, and it seems to vary between 35 and 36 FPS average. So async, I've got 35.26, 36.55, 36.52, and non-async 36.52, 36.58, and 36.64. So I think it's just margin of error. I don't think there's actually that much difference with having async compute on, which means I'm guessing the asynchronous part of the queue, from what we see here, these parts must be getting done pretty quickly, or possibly it would mainly be with the fluid simulation. We can't get a frame rate out of that because the fluid simulation is only done on the demo. So I think async just doesn't make much difference here, because these bits are getting computed so quickly, even if you're not using async. So it'll be interesting to see where async does cause big FPS differences, because so far, including in last week's video, we didn't see any real difference in performance with async on or off. So next up, what we're going to do is re-enable async compute, and we're going to put reflection mode on traditional. So here we're on the demo, which will be probably a lot more impacted than the graphical test, because the demo has a lot more advanced ray tracing used in it, so having that missing should affect this quite badly. There's screen space reflections there. Very grainy and inaccurate. Horrible cube maps in the windows. Oh wow, what is going on there? That weird shadow on the ship doesn't look quite right. Oh god, missing reflections. Reflections cutting off. I think there's some screen space on the ship, but it's mainly cube maps. Yeah, you can really tell the drop in quality. Missing global illumination as well. The shadows look very similar to the ray tracing one. It's not too much of a difference there. The more I watch, the more I realise how freaky this demo actually is. Like the music and the still robots. Yeah, you can really see the inaccuracies there on that bottom bit near the landing gear. Just the reflection just disappearing and barely there. Wow. Looks like the fluid simulation is fairly similar, if not the same. Yeah, it still looks good, but you can just tell the reflections are just, yeah, bad. Here we are on the graphics test. So this should all be using standard rasterization. Although I still see some blur there. A lot of weird blur. It could just be screen space. You can definitely tell the global illumination is missing. And screen space reflections there. Backed up by cube maps. You can just see the immense difference on the ship. It's literally just using a cube map, I think, with the sky on it. So no reflections from any of the active geometry. Nothing. It's just the cube map. Wow. Yeah, you can really see the limitations of that. So I imagine that's the same cube map, possibly, that's being... Oh, that one in the background is nasty. Oh my god. It's possibly the same cube map that the rays are sampling on rough surfaces. My god. Yeah, that rough sort of red part of the ship still looks fairly okay. But then again, I think even the cube maps are built from rays, from what I was reading, from what I understand. So even the cube maps will be of worse quality. And we only got up to 40 FPS. It's only, what, 4 or 5 FPS increase? Yeah, really not that much of a difference in frame rate. Must be a lot of the traditional rendering that's costing quite a lot there. The ray tracing actually seems to be a minimal impact on the FPS. Very strange. So yeah, that shows a sort of advantage you get from ray tracing. In fact, what we can even do is just go to no reflections at all and see what that looks like with the demo. So again, this is going to look very similar to the rasterized version. It might even look a little bit cleaner because there's no screen space reflections. Yeah, just very basic lighting. Yeah, there you go. You can tell just no reflections at all. Just a basic opaque texture there. And some lighting on it. Specular. The ship looks completely different. It might just be cube maps only. Or just a completely blank texture, okay? Oh yeah, there's just specular on it. So I'd have thought they'd at least kept the ship silver, but it, yeah, just turned into, yeah, painted black, so that's interesting. But it does generally look cleaner than the rasterized one because there's no screen space errors or anything like that. And getting rid of those horrible cube maps on that glass looks far better. Again, the shadows look very similar. It'd be interesting to see what the frame rate difference is. Yeah, the scene looks so much less alive. And look, there's no reflections even on the particles. Wow, look at that. Got a very diffuse looking liquid. Ugh. It just looks like sewage. Wow. So quite a difference there. And the graphical test itself looks even worse. Yeah, it just looks like for some of the reflective surfaces they've just completely blanked out the texture entirely. Which is an interesting way to do it. Of course, it's just a benchmark and a demo of technology, so they're not really building it around being able to flick the settings on and off and still have it look good. It's just a demonstration of, I'm guessing, where the reflections are being handled. Because if you go to no reflections, you can quite clearly see where all the reflective surfaces are because they're now all completely black. So that actually makes sense. So I'm guessing that's the metal map, the metalness map, doing those specular reflections. Oh, some weird glitching there. Looks like some ordering's getting a bit off with the transparency effects. Must be when you switch off all the reflection effects, the ordering algorithm gets switched off or gets a bit mixed up. Now this has to have a higher frame rate to it. 119 FPS. So yeah, a lot of the compute work is being just done on the reflections before you even start doing ray tracing, because when you've got reflections on in ray tracing, it brings it down to 40 FPS and then 35 when you're doing the reflection mode. Oh, of course, there's separate things to disable the ray trace shadows and light shafts here. So these are all rasterized, and then the shadows here you can actually disable. So I imagine actually the ray tracing was still occurring. So if we go back to traditional reflections and then run another test, but with the ray trace shadows off, we should get a much higher frame rate because the ray tracing was still technically on. Yeah, so let's run that again. I won't show it again, but I'll run it again with traditional reflections and disabling ray trace shadows. So even with everything off that could be doing any ray tracing, we're still only getting 48.31 FPS. So I think even with disabling all of this and having reflections on traditional, I think even the rasterization reflection is doing so much heavy lifting, which is unusual. It's only when you flick reflection completely off that the frame rate will jump up. So it must be a lot of the pre-ray tracing preparation that takes up quite a lot of the frame rate there. You know, all this sort of stuff. Because yeah, the ray tracing is only a relatively small element of it, and a lot of it is part of the preparation and the other work. So it must be a great deal of work goes into the reflections before the RT even hits, because the ray tracing only takes off about 5 frames average, which is really interesting. It's most likely that over the past 5 years as well, the way ray tracing works has been changed quite considerably, and the ray tracing hardware and drivers are just a lot more efficient now, and there's a lot more efficient way of preparing all of this. Okie dokie, so that is the custom settings. Let's just see if we can do a normal run and get a score out of the end of it. So interestingly, with the default, we have 104 FPS and 22,466 points. I imagine what's happening is that some of the settings that I've cranked up in the custom test, probably the reflection filtering being up at high is probably what's causing that frame rate to drop so heavily when reflections are on. But still, it's funny that even with that on, the ray tracing still only takes another 5 FPS off of it. It could be just a reflection of how efficient ray tracing is now. And then it also gives you a nice little estimated game performance here. So Battlefield 5 of the time at 1440p. Well, it used to tell you how it would run. Doesn't say that anymore, it just says no data available. But it used to give you a sort of general frame rate of what you would get in those games based on this result, and that's quite handy back in the day. So now we can look at the overall score. Just about matches up with a premium gaming PC, so not a bad result. And that brings us to the conclusion of Port Royal, and it's a pretty damn good benchmark. It's very much of the time, very 2019, very much early ray tracing sort of time. Quite a bit of nostalgia for that sort of era, back when I did my first ever ray tracing video on Battlefield 5 with my 2080. It's a good time. It's a really enjoyable benchmark to go through. Let me know what you think in the comments. How does it stack up with your hardware? Let me know if I've gotten anything wrong. Again, check out all the links in the description about some of the things we've been looking at. And next week, I think we'll be taking a bit of a dive into the DirectX ray tracing feature test itself, which goes a little bit more in depth. It was released about a year and a half after Port Royal, so we can look at some of the more details of ray tracing and use the interactive mode to capture some of the differences and see any advancements that were made over that year and a half. So I think Speedway handles ray tracing as well. I think Speedway came out in 2022, so we will look at that in a couple of weeks and we'll get a much more accurate representation of where ray tracing is now. Things advanced quite a bit over the years with DirectX ray tracing and Vulkan ray tracing in general, very, very quickly. So, and also Solar Bay looks like to have some ray tracing, ray trace cross-platform testing, and I don't think we've looked at Solar Bay yet. So we are working our way through the ray tracing benchmarks. Keep an eye out for that. That was Port Royal, and a little bit of a look into how ray tracing works. So thanks for watching. Hope everyone's staying safe, and I will see you in the next video.